Okay, so today we're going to discuss JADE, which stands for an adaptive differential evolution with optional external archive. Let me begin by explaining how basic the algorithm works. So basically, it's a method that optimizes a problem by iteratively trying to improve a candidate solution with regard to a given measure of quality. So let's see at some basic operations. At first, the initial population is randomly generated according to a uniform distribution. After that, D enters a loop of evolutionary operations: mutation, crossover, and selection. At each generation, we create a mutation vector based on the current parent population. After mutation, a binomial crossover operation forms the final vector. The selection operation obviously selects the better one from the parent vector and the trial vector. So the original is generally kept fixed in different D algorithms, while their crossover may have variants other than binomial operation. So now Luba will tell you about main features of JADE.
So let's consider main features of JADE. Firstly, unlike in differential evolution, in JADE we change mutation factor and crossover probability at every iteration. We use normal distribution for generating mutation factor and Cauchy distribution for crossover probability. At first, mean and location parameter equal 0.5. But every time our parent vector fails in selection process, we added to an mean and location parameter. And then we calculate them using following formulas. So our new mean for mutation factor will be equal to 1 minus C, where C is constant from 0 to 1, times our current mean, and plus arithmetic mean of all our successful means that we saved previously. And crossover probability is calculated in the same way, but instead of arithmetic mean, we use Lemaire mean. So mutation vector is also calculated in other way. Firstly, we need to find p% best current vectors in our population. Let's call them p best. Then we randomly choose 3 vectors, x p best from our p best vectors, x1 from the population in general, and x2 from our population and the archive. And then our mutation factor is generated as follows. You can see the formula where xi is our current vector and fi our current mutation factor. So to test our algorithms, we chose Rastringin function. It's often used to test optimizational program algorithms because it's hard to find its global minimum because it has a lot of local minima. And on this at this slide you can see the results. After 100 executions. The space dimensions were equal to 100, number of iterations 2000, and population size was 20. So that's all. Thank you for your attention.
Okay, thank you very much. Anyone has any questions?
No.
Okay, so if no questions, let's go to the next presentation.